Hello everyone, welcome back to Chapter 5, Chemical Quantities and Reactions. In Section 5.2 we're going to talk about molar mass. And I will tell you right now, if you don't have a periodic table in front of you, you're going to need it because we're going to be looking up some atomic masses and things like that. So make sure you have a periodic table, either the one in your book, turn to that page, or print the one off that I have for you under the Start Here materials. Alright, so molar mass. Basically, the molar mass is how much mass there is in 1 mole of an element. The numbers that we see that tell us the mass, for example, when we're looking, remember that the mass numbers are these that are on the bottom that are usually have a decimal point or something like that because they're an average. These are in AMUs, which is an atomic mass unit. When we are using the mole concept, which is what we basically use for all of our calculations in chemistry, we are looking at the molar mass, which is this atomic mass here, basically times the 6.02 times 10 to the 23rd. So we can use this as grams. So basically what I'm saying is that we can use this same number that we look at. It's an AMU for an atomic mass, and we can say that 1 mole of those atoms has a mass of 12.01 grams. Okay, and so we allow that allows us to make real world calculations, because I couldn't measure 12.01 AMUs, like 1 atom of carbon, but I can measure the mass of a mole of carbon, and so we call that the molar mass. And so that's basically that same exact number, just expressed as grams. Okay, so the 6.02 times 10 to the 23rd atoms of carbon, which is 1 mole of carbon, is the same as 12.01 grams of carbon. So the atomic mass expressed in grams is the molar mass. So 1 mole of silver has a mass of 107.9 grams. I get that from the periodic table, and if you look at element number 47, you will see that that's exactly what that says. A mole of carbon is 12 approximately grams, and a mole of sulfur is approximately 32.1 grams. So that's where we find the molar mass, is we look at the periodic table and we read that mass number at the bottom. And remember, we're talking about molar mass, so we're talking about the mass of an Avogadro number of those atoms, 6.02 times 10 to the 23rd. So using that, look at our periodic table, and we find potassium, which is the element K, it's number 19, and we see that 1 mole of potassium is equal to 39.10 grams. 1 mole of tin, which is SN, which is number 50, is 118.7 grams. All I'm doing is I'm looking on the periodic table and finding these elements and then looking at their mass. And so 1 mole of calcium atoms, calcium is number 20, is 40.1 grams. All I've done right now, no calculations, all I've done is I've looked those up, and that's what I found on the periodic table. Okay, and depending on how you round, okay. Now, so if we are going to do molar mass, we get the molar mass, and in this case, like a mole of a molecule, if we were going to do that, we would obtain the molar mass of each individual element. We would multiply each molar mass by the subscript in the formula, and then we add them all together to get the molar mass. So the example here is C₂HO. Right? So we're going to see C₂H6O. 1 mole of carbon we know is 12 grams. 1 mole of hydrogen is 1.01 grams. And 1 mole of oxygen is 16 grams. How do I know that? I look at the periodic table. Okay? That's where that information comes from. All right? And so once I find that, the second step is I multiply it by how many moles of each one is in the formula. So I've got 2 C's, 6 hydrogens, and we know I only have 1 oxygen because 1 is understood. And so 2 times 12 is 24. 6 times 1.01 is 6.06, and 1 times 16 is 16. Now I add all of those up, and the molar mass of C₂H6O is 46.1 grams of C₂H6O. So the molar mass of this molecule is 46.1 grams, which is the sum of all of the molar masses. Notice that the molar quantity or the molar mass is different depending on which of these substances. For example, sulfur by itself is, about that much. Okay, iron this much, NaCl that much. Look how much more you get of some of these bigger molecules. A mole of them is much more, and many more grams than just an element, for example. And it just depends on what their mass is. So let's try a couple of these. Put me on hold and go ahead and try these. If you don't have them, pause it, and then when you come back, we'll look and see. All right, so, and remember, you're going to have those detailed instructions at the end, but for right now, I'm just going to work them, okay? So I'm going to do A first, okay, and I have K2O. So I have K, and this is just how I do it. I've got K, I've got how many Ks? 2, all right? And so I'm going to look up what the molar mass of potassium is. Remember, it's number 19, so it's 39.1. All right, and oxygen, I have 1 of those, and oxygen, which is number 8, is 16 grams. Should put my units. Okay, so what I have to do is I have to say 39.1 times 2, which is 78.2 grams, and then 16 grams. And then when I add those together, I get 94.2 grams. So that's what I'm getting for K2O. For aluminum hydroxide, now this one gets a little more complicated because you remember that if I have a 3 right there, that means I multiply everything in here by 3. So in aluminum hydroxide, I have 1 aluminum, and I have how many oxygens? 3. And how many hydrogens? 3. All right, so I look up aluminum, and aluminum is number 13. So that is 26.98 if we're going to be exact. So that's going to give me 26.98 grams of aluminum. And oxygen is 16. I think that's 48. I'm doing that one in my head, so if I'm wrong, sorry. And then 3 times 1.01 should be 3.03 grams. All right. And so then I'm going to add all of those together. So 26.98 plus 48 plus 3.03. I get 78.01 for the aluminum hydroxide. All right, so let's see how we did. Now they do them like at the same steps. All right, and so yeah, we got 94.2 K2O, and we got 78 grams aluminum hydroxide. So we did pretty good. All right, let's try another one. Oh, Prozac. Sometimes during finals, I think I need Prozac, don't you? All right, C17. Just kidding. C17H8 F3NO is an antidepressant that inhibits the uptake of serotonin by the brain. What is the molar mass of Prozac? Okay, right. Well, we've got C, and it doesn't matter how big it is, we got this. We've got a C and an H and an F and an N and an O. All right, so for C, we have 17, and C is number 6, and it's 12.01. And it's just the way I do it. You can go ahead and multiply that out if you want to. I usually just get all my stuff and then do all my calculating at the same time. Hydrogen is 18. That's going to be times 1.01. I can usually remember hydrogen. Fluorine, which is number 9, is 19. Oops, I don't have 19 of them. I have 3 of them. Let me see if I can erase this thing. Ooh, I did. All right. So proud. All right. So 3. Oh, of course, and then I have to mess it up, right? And I was doing so well. All right. 3 times 19. All right. I've got 1 nitrogen and 1 oxygen. I remember oxygen is 16. Some of these you'll use them so much that you'll remember. And I think nitrogen's 14. Yeah. 14.01 if we're being exact. Okay? All right, so now we go to our calculator, and 17 times 12.01 is 204.17. 18 times 1.01 is 18.18. All these are grams. 3 times 19, 57. And then 14.01 and 16. All right, now 204.17 plus 18.18 plus 57 plus 14.01 plus 16 should give us 309.36 grams of Prozac. So you probably would not want to take a gram of Prozac. 309 grams of that would be pretty big. That would be like filling a sandwich baggie or something. So that's why you'll see in medicine that we often talk about quantities such as micrograms or milligrams, which are like 0.3 grams would be like a milligram of Prozac. All right, let's see how we did. $309. Okay, I'll take that. We did pretty good, didn't we? We used the decimal places, but they rounded like they were supposed to, so there we go. Molar mass conversions are where we're going to use these. These are the ratios that we use the molar mass so that we know that 1 mole of, for example, methane here is the same as 16 grams of methane. So you can write the conversion factors here, and remember they can go either way. 16 grams of methane over 1 mole, or vice versa, as we can do all of these equalities. And so when we solve these problems, what we do is we state what we are given and what we are needing. We write the plan to convert them. We determine the masses, write the conversion factors, and then set the problem up and solve it. So a box of table salt has 737 grams. You can actually look at these and tell. 737 grams of sodium chloride, and the question is how many moles of sodium chloride are in a box of sodium chloride or table salt. Okay, so we can do that because that is we're given 737 grams of salt. What we need is moles of salt. Okay, so if we know the grams of salt, we can do a conversion. We know grams is going to go on the bottom because it's got to be whatever came before sodium chloride. How many grams are in 1 mole? Well, let's see. Sodium, I think it's 23. Let's see. Yes, number 11 is 23 grams. It's 22.99, but close enough for us, right? And then chlorine is 35.5 grams. So sodium chloride looks like 58.5 grams. So 58.5 grams of sodium chloride in 1 mole of sodium chloride. All right, and so then we know that cancels. That's going to leave us with moles of sodium chloride. So now all we do is divide everything on the top by everything on the bottom. So 737 divided by 58.5 should give us 12.6 moles of sodium chloride in a box of sodium chloride. And I believe we did that right. So whenever we're going to do a calculation in chemistry, usually you have to go through moles. I tell my students that it's kind of like if you want to get anywhere from the south, you've got to go through Atlanta. So to get anywhere in a calculation, you have to go through moles. If you're given grams of something, you use the molar mass to convert that to moles. If you want to know how many atoms that is, you have to go to moles first, and then you can use Avogadro's number, and you remember what that was, 6.02 times 10 to the 23rd, to get to atoms. Now, if you have a formula, moles of the elements, you just use those subscripts like we just did to get to moles of compounds. And then you could figure out grams of the compound, or like we're just calculating, or you could do molecules or formula units. And you remember the difference? Formula units are for what? Ionic compounds. And these are for what? Covalent molecules. Allyl sulfide is the smell of garlic. It's C₂HO. And so what they want us to do is calculate how many moles of that are in 225 grams. All right, you got to watch how they ask the questions. Sometimes they put what you're given at the end. And so in this particular case, we're given 225 grams of allyl sulfide, C₂H10S. And it wants to know how many moles are in there. Okay, so we know that grams of the allyl sulfide will go down here. We know that. Why? Because grams is up here, it has to be down here. Always follows. So that means mole, 1 mole of C₂H10S will be up here. All right, so now we've got to do what? Calculate how many grams of allyl sulfide are in 1 mole. So we've got C, H, and S. C is 12, H is 1, and sulfide is number 16. It is actually 32 or 32.1. We'll just say 32 for now. So we got 6 carbons, 10 hydrogens, and 1 sulfur. That's 72, I think. I never trust myself on big numbers. 72, all right. So 72 plus 10 plus 32 gives us 114. That's what I got. Okay. So 1 mole of allyl sulfide should weigh 114 grams. And so grams cancel. And so we should then be able to say 225 divided by 114 gives us 1.97 or 2 moles of C₂HO. They have 19.7. Is that right? I don't think so. I think we did it right. 225 divided by 114 is not 19.7. It is 1.97. So the book was wrong and we proved it. I love it. You can prove stuff in math, not science. So actually your learning check is incorrect on that one. It should be 1.97 moles. Isn't that awesome that we got it right and the book got it wrong? And that's the end of 5.2, a good place to end, I think, where we talked about molar mass and we used mole quantities, mole equalities to work problems so that we can convert between grams and moles. And we can do moles, or we can do atoms, or we can do molecules now that we've gotten through this. All right, I'll see you soon.